All right. All right. So, one thing I forgot to really emphasize when testing collections is, wait, did I hit record? Yes. One thing I wanted to make sure I emphasized was, so how I did the layout for testing collections. Remember, I had the nested class. I had my test class, and then I had a nested class for the empty tests, and then in that I had a nested class for the singleton tests, and then I had a nested class for like the more general case of when there's several things in the stack. You'll notice, if you go and look at the code, for example, let me go up here. See, look at the first two tests. Push, empty, returns true. Push, empty, results in a new top. Right? Those are two good things to test for push. That's probably sufficient for testing push. But when I do the nested class, you'll notice I have push, empty, returns true, but I don't include push, empty, new top. I got rid of it. Now, I didn't need to get rid of it, but the reason I removed it is because if you were to go down to the singleton one, well, it's not there. If you looked at the peak one, which I've got right here, push, empty, new top, and this would be the singleton, peak, singleton, returns top. And look at the code. Look at the test code. With the exception of the value, it's the same. I am effectively testing the push new top in the singleton tests. So if I included it, it would be a redundant test. So that's why it was eliminated, because it's going to get implicitly tested when testing peak. And this is really also the consequence of all of these tests, all of these methods, are so interconnected that you really can't test one with the other. So they both test the same thing. So for consistency, I got rid of the push, empty, new top. And same with like push, singleton, new top, because the many would also similarly do that same thing. Cool. So that was just a note on the collections unit tests. All right, so links and linked structures. Sometimes, I'm going to warn you, two big warnings. Sometimes people refer to these things as linked lists. Do not call these things linked lists, because linked lists, especially in the context of Java, has an entirely different meaning. This is a linked structure, and you could build linked lists with a linked structure. But right now, we are talking about the underlying idea. So this whole topic right here, the links and the link structures, I am not teaching you a new abstract data type. That's not what this topic is. This isn't a new, like, oh, it's like a stack. No, this is not analogous to something like a stack. This is analogous to talking about the array, the underlying container. So we're going to build something that's similar to an array that we could then use to implement a stack, for example. And we will, that's like the next topic. If not the next, but it's coming up. So arrays, they have fixed sizes, right? We saw it wasn't that big of a deal. We have our expand capacity, whatever. We can address that. But arrays have fixed sizes. Arrays are also, traditionally speaking, stored in contiguous memory. You know, memory addresses x through x plus 10 is a length 10 array, right? Traditionally speaking. Technically in Java it's not like that, or a lot of other modern programming languages, but traditionally speaking that's the idea of an array. And it's at least treated as if it is contiguous. And also, if I have an array and I removed something from the middle of it, I would have a gap, right? And then if I wanted to close that gap, I would have to like shuffle things around, right? And these aren't bad things. It's just as a consequence of what arrays are and how they work, that's the state of things. These are not bad things. They're just the way it is. We could build, instead, link structures. So here's an example link structure. They're made up of nodes. Okay? In this particular picture right here, nodes are represented by the boxes. And the boxes store some data, some element of whatever, I don't care. And in addition to the nodes having some data, they have a link. That link is just a reference to some subsequent node. And in this particular example, I have a reference variable called head that references the head of this link structure. Note, head is not a node. I want to be very clear about that. Head is not a node. What is head? Who can tell me? This isn't a trick question. I've been emphasizing this forever. What is head?
The reference to a node.
The reference to a node. Head is more like the arrows between the nodes. Head is a reference that gets you to a node. Unlike arrays, link structures have no fixed size. There's nothing stopping me from going to the end and being like, add a new node, and then a new node, and a new node. And I could do this forever. I'm not going to run out of room. I don't need to expand capacity ever. That array, I mean, it's not an array. There's no fixed size. And there's no need for things to be stored in consecutive memory. Like in an array, traditionally speaking, if you are at index I, and I asked you, where do you find the next element? What do you say? I plus 1, right? It's the next spot. With a link structure, it's the next thing is, well, follow that reference to the next node. Arrays didn't have this built-in like next idea because it was like implicitly there as a consequence of being in contiguous memory, traditionally speaking. And data, there's another interesting thing. I could, and we're going to see an example of this, I could add something to the middle of this structure pretty easily. Let's look at that. See that? The gray and the blue. I could add an element between those two. Imagine I have a link structure of 1 billion elements. Imagine I have a link structure, or I have an array of 1 billion elements. And I want to, here, I've got a simpler idea. We have an array of 1 billion elements, and I want to add something to the beginning of that array. I've got to move all 1 billion down 1 to make room for the new thing at the front. If I have 1 billion elements, I have to move all 1 billion of them. If I have n elements, how many do I have to move? N. With a link structure, here's how I insert to the front. And we'll see this in an example in a moment. I'm just jumping ahead. I could say, okay, I have a new node. I put the data I want to insert to the front inside that node. I say, hey, that node, you reference what head references. And head, you now reference that new node. And we just inserted to the front. I didn't have to move anything. I added the one new node, a couple simple little operations, but I didn't have to shuffle anything down or anything. We'll see an example of this in one moment. Let's jump back to a node. A node is the simple, basic building block of the link structure. And the node we're going to talk about is going to be a singly linked node. Each node has one link to a subsequent node. And here's the idea of the node. The node, which is a box, I've represented as a box, has the data and the next. Data, it'll be a reference to some data. And next will always be a reference to some other node. Or potentially null if it's like the end, or if there's no successor. That's the idea. That's it. This right here is the basic building block of the node. It's got two fields, data and next. Data, a reference to the data to be stored. To compare this to the array, this is the element stored at some index in the array. This is the data actually in the array, in the cell of the array. And next, well, like I just said, there really is no analogous thing in an array because the array has it like just built in with how the array is built, where it's just, well, index I plus 1 is the next thing. So let's start inserting things into the link structure. With a reference to the head of a link structure and the two fields, data and next, here's a question. Okay, how would I access the first node's data? Here's how I would do it. Okay, I have head. Head is a reference variable, and it's got some data in it. So I could say, head, give me your data. And then it would work. If I wanted the one after head, I would say, okay, head, give me your next node, give me your data. If I want the third one, I would be like, okay, head, give me your next, give me your next, give me your data. And so on and so on and so on and so on. If I want to add something to the front, well, let's have a look. Given a reference to the front of the link structure, head, and a reference to the node to be inserted, node. This is the situation I have. That blue node, I want to insert into my link structure. This is a very simple link structure. It's got 1, 2, 3 elements in it, that's all. The yellow, gray, and black. Remember, head is not a node, it's just a reference to that node at the beginning of the link structure. So here's what I'm going to do. I'm going to say, okay, node, the one I want to insert, set your next to be head. Now when I do that, remember, that doesn't mean that the node's next references head. No, it references what head references, right? That's what we have here. So node, your next is going to be referencing what head references. Just like that. Then I say head, you now reference what node references. Like that. Now, if I ask you what the head of the list is, the head of this link structure, what color is it? Blue. Why? Well, because it's pointing right there. It was yellow a moment ago, but we just inserted something to the front. Imagine that list, that link structure was 1 billion elements long. I didn't have to move any of those 1 billion things. I just had to update what head referenced, what node referenced, and what head referenced. That's it. Actually, not what node referenced, what node's node is next referenced. But, yeah. Any questions about that? Adding to the middle, or some, when I say middle, I mean just some arbitrary point in not the front or the end. So let's say I want to insert, somehow I found the spot I want to insert the node. Actually here, let's do this as a little exercise. I want you to take a moment to think, maybe even talk amongst yourselves. Let's say I want that blue box to end up being between the turquoise, what color did we determine that was again? Turquoise. Turquoise, yeah. Between the turquoise and black one. I want the blue box to come between those two. And right now, I have head and node. Actually here, I'm going to jump ahead and we're going to say, let's say we are in this state here. Right? Where I have head, I've got current, where current is the node that I want the new node to come immediately after. Right, so we found the insertion point. This is what we have. We have a reference to node, we have a reference to current, which is the node that node is supposed to come immediately after, and a reference to head, but the reference to head is not going to be helpful for this stage. Take a moment and think, how would I insert that there? I'll give you a moment to think about that. You can talk amongst yourselves. It's not hard, but there is a trick to it. All right, who's got an idea? Who wants to try? I want to see if we can find someone different. You're participating too much, I know. What do you say back there?
Have the blue point at the black.
How? I have a reference to node and a reference to current. I'm not going to ask you. He told you the answer.
I actually did. So
all right.
Good. So you
all right, how about we'll give you a go then.
You'd set blue to cyans, to reference cyans next.
Okay, so what you're saying is, do that.
Yeah.
Right, so you say, okay, node, your next is current's next. Okay, then what?
Then you set current's next to blue. You set cyans next to blue.
To that?
Yeah.
Raise your hand if that's exactly what you were thinking. Now, be honest. Raise your hand if what you said was, we'll have current reference node, and then have node reference the black ones. Raise your hand if you did it in that order in your mind. Okay, well, I don't believe you, because I've been doing this for years, and usually that is typically what people think. But who can tell me why that is a terrible idea? What do you think?
You lose reference to what current is referencing.
Exactly. If we did this by saying, okay, current, your next references node, right? This arrow would then point to the blue one. But the problem is, nothing would be pointing to the black one. Meaning, we've lost reference to the black one. So then when the next step comes along and I say, well, okay, now how do you set the blue ones to the black one? You go like, we'll set it to the black one. And I go, how? You go, well, it was current's next. Well, it was, not anymore. You lost reference to it. You have no reference to it. It's gone. It's fading into oblivion. What's going to happen to it? The garbage collector is going to come and take care of it, and all your data is gone. Imagine that node had a million successors after it that had all the critical important information for your program, and suddenly it's all gone. Oh no. So you have to be very careful not to lose reference to things. So the order in which you do things here really matters. So you have to say node, your next is current's next. So node, your next will be what's current's next. Well, that's this black one. And then current, your next is now just, well, what node it is. And there we go. Now it goes, what color is that? Light blue? Light cyan, light blue, some weird green, teal, blue, black. That's the order. We inserted it where we wanted. Good. And it turns out, adding to the end, is actually exactly the same as adding to the middle. And here's why. Imagine for a moment current wasn't pointing here, it was pointing to the black one. In a situation like this, the end of the list, the end of the link structure, its next will reference null. It references none, because it's the end. So in that case, if we follow the same algorithm, it actually achieves the same thing. We say, okay, node, your next references current's next. Well, in that case, the black node's next is null. So current, or pardon me, the new node to be inserted next gets sets to null. And then current, which is the black node's next, gets sets to node. So it just gets added to the end and it even sets null perfectly. So that's awesome. So it turns out adding to the middle and adding to the end is actually exactly the same set of instructions. But adding to the front's a little different, which we just saw. But adding to the front is pretty easy. Any questions? Any questions about that? Yeah.
Do you have to add on to the back the same way you do in the middle, or could you just ditch the null reference, add on the last bit, and then do a new null reference for the last?
You could, but I'm lazy to write a different algorithm. I would just write the same algorithm once and I'm happy. But you could do it that way, yeah. Yeah.
What's the advantage of an array over this?
The advantage of an array. Well, you know what? We're going to talk about that. I think that's the next topic. I'm going to check 1 second. No. The next topic. We're going to have a chance to really think about the linked implementation versus the array implementation. So I don't want to answer it now because it'll be spoilers. Because I want to have a chance for everyone to kind of think about it. The end of the day, though, the biggest advantage of an array is the simplicity. You get it kind of just as a consequence of how memory is laid out. Array is just some contiguous, traditionally speaking, contiguous chunk of RAM. Start at memory address X and go to memory address X plus 10. Those 10 memory addresses, that's your array. Boom, there. It's just there. I didn't need to code anything up to create this, because for this I need to define what a node is. I need to update all these references. Where the array, it's just kind of baked into the computer. So there's the advantage there. But we're going to think a little bit more about this as we go. The fact that your mind went there, though, fantastic. But I don't want to spoil it for everybody. Other questions? All right, adding to the end. Oh, wait, we just did that. Remove it. Removing from the front is going to be the easiest of all these. Head. Right now you're referencing that light blue, whatever, cyan, whatever color that is, teal. No, don't reference that anymore. Reference, if I ask you, what color is heads next? You say what? Yellow. So what you say, okay, head, you reference heads next. That's all it is. Boom, gone. You've removed from the front. And now, if I ask you, what references that aquamarine color? It's going to be a different color every time I talk about it. What references it?
Yellow, but
No, there's no, yellow doesn't reference anything.
yeah, that's my so
Oh.
when nothing is referencing a node or they're just gone.
They are, so what will happen is we lose reference to it. So there will be a point in time where it exists in your memory somewhere, but you have no way to get back to it.
Okay.
So it exists, but it's just kind of taking up space. It just exists. Because of that, you're wasting memory. And after some amount of time, the garbage collector will come along and be like, okay, well that's not actually referenced by anything anymore, meaning it can never be used again. So we're just going to free up that space so it could be used by something else. Yeah?
So that why like C is no longer safe memory? Safe memory.
So in C, depending on whether you're working in the stack or the heap, memory space, which is the whole thing that we will kind of talk about a little bit later, depending on how computers, your programs like to know how much memory they need before they run. But sometimes, if I need to make an array, for example, and I need to read in a file, and based on the contents of that file, I want to put the information in an array, I got a bit of a problem, because what if there's 10 things in that file or 10,000 things in that file? My program can't know how much RAM it needs. So at run, there's a way we can do finding out how much memory we need at runtime and tell the program, okay, 10. We need information for 10 things. Go find 10 units of RAM we can allocate for this, right? And then, when we're done, we need to delete it, because we're done with it. We don't need it anymore. If you don't delete it, you create a memory leak, because C++ doesn't have a built-in garbage collector. It just doesn't have that. But garbage collection actually takes computation time, so it actually slows things down. So you have to be very careful. But that type of stuff, there's a million reasons why it's not memory safe. But C++, you'll create memory leaks because it has no garbage collector. But it's ultimately the same thing, it's just Java doesn't care. It's like, yeah, whatever, I'll delete it later, I don't care. So let me ask again. As of right now, what references that blue-green node? Nothing. If you're like, well, yellow kind of, but my answer to that is absolutely not. Because you're looking at that arrow that points to yellow. Yellow doesn't know anything about the thing that came before it. It doesn't. Something got to it, but it doesn't know what came before it. It doesn't care. Each node only knows about its successor. It has no knowledge about its predecessor. It doesn't know, the node doesn't know if it's at the beginning of this link structure or at the end. I guess it could know if it's at the end if its next is null, fine. But it doesn't know where it is. All it knows is its data and what comes next. And then removing from the middle, well, here you could do it with only one reference. Imagine we just had previous. You could say previous, your next is previous is next. That's all. Removing tends to be pretty easy to do with link structures. You just got to be careful with the order in which you do things. And removing from the end is same thing as removing from the middle. It's just the next would have been null. All right, we'll end here.